Last time you walked me right up to a door and then, entirely in character, strolled off into the dark before you opened it. We'd thrown out the whole idea that one charge reaches across a gap and grabs another. In its place, you handed me the field. Charge fills the space around itself with a real, invisible thing. And you left me a promise on your way out.
I did leave a promise, and tonight I keep it. Let me stand the stage back up first, lightly, because it all leans on one picture from last time. A lone positive charge sprays field lines out in every direction at once, like spines off a sea urchin. Faraday's lines streaming out of the plus, diving into the minus. And where they crowd close, the field is strong.
And the lines don't only stream out of the plus, they dive into a minus if there's one about. Out of the source, into the drain, same as you drew it last time.
Out of the source, into the drain. You kept it. Tonight, though, one lonely charge and its outward spray is nearly all we lean on.
That was the part I loved. The strength wasn't a separate number bolted on, it was only how tightly the lines were bunched. Up near the charge, they pack in dense, and the push is fierce. Far out, they fan wide and thin, and the push goes soft. So that's the whole toolkit I'm carrying in tonight. Now, the promise. Remind me exactly what you dangled on your way out.
I told you we'd learn to count the field, and that the counting itself would harden into a law. I had you picturing a bag drawn around a charge, any bag you like, and tallying the lines that punch through its skin. That tally, I claimed, would come out to something solid and fixed. So hold the picture, a charge, the lines spraying off it, and a closed surface wrapped around the lot.
I've been turning it over since, and I'll admit that on its face it sounds absurd. You want me to count a thing I can't see? Field lines, threading through a surface I made up out of thin air. That's two kinds of imaginary stacked one on top of the other. How does counting my own invisible doodles through a bag that isn't even really there tell me one solid thing about the actual world?
It sounds absurd right up until it doesn't, which is roughly the shape of every good idea. But your objection's a sharp one, so let me take it seriously before I answer it. You're right that the lines are half a fiction. I told you last time the field is smooth, an arrow at every single point in space. The lines are a drawing you lay on top of that smoothness.
A drawing on the smooth thing, so the smoothness is the truth, and my lines are only my sketch of it.
The smoothness is the truth. The lines are how you read it off, which is why the sketch unsettles you. A sketch you can pad or thin at whim.
That's exactly the worry, and it's a bad one. If the lines are my drawing, then how many there are is my choice. I could sketch 10 lines coming out of a charge, or 10,000, depending on my mood and how sharp my pencil is. And then the number poking through any bag depends on how busy I was that morning. That can't be a law. A law shouldn't care how much ink I felt like spending.
It doesn't, because you sign one contract at the start and never break it. You agree on a rate. A stronger field earns more lines, packed tighter, in fixed proportion. So many lines for so much field strength, always the same trade, and you never cheat on it in one corner of the picture. Sketch 10 lines or 10,000, it makes no odds, as long as the rate holds everywhere the same.
So the individual lines are bookkeeping, but the rate nails them to the real field. And once it's locked in, the count means something after all. All right, I can live with that. The count through a surface is really tracking the field strength times the area I hold up to it. Which brings me straight to what I keep snagging on. Area of what? There's nothing solid out in that field to have an area.
Then put the field down for a moment and go stand in a draft. Open window, wind blowing in through it, and ask the plainest question there is. How much wind gets through the window? Two things set the answer, and only two. How hard the wind is blowing, and how the window is facing it. Nothing else in the world matters to that one question.
Only two things. The wind's strength and the window's angle. Not the room, not the paint, not the curtains.
Not one other detail. Everything else sits the question out. So which of the two would you have guessed on your own?
The wind part I'd have guessed cold. Blow harder, more air through. It's the facing part that does the quiet work. Turn the window flat, square on to the wind, and it catches everything the wind's got. But swing it edge on, so the wind streams past its rim, and hardly a breath gets through, though the wind never changed and the glass never shrank. Same window, wildly different amount of air, purely on the turning.
The facing is the whole subtlety, and you can feel it on your skin, which is why I reached for it. So carry that back to the field now, with the window turned invisible. Hang an imaginary pane out in the field, a little hoop, a picture frame, whatever you like. The field lines thread through it exactly the way the wind blew through the window. And how many get through rides on how you hold it.
So if I hold the hoop square on to the lines, the most of them stab straight through it. And if I turn it edge on, the lines skim flat along its face and pierce none of it. Same hoop, wildly different number through only on the turning. The wind and the window all over again, minus the wind. And now, let me guess, this is where you finally ask me to count them.
This is where I ask you to count them. Tally up the lines that punch through the hoop. That number, the field strength, times the area of the hoop you're holding square on to the lines, is the thing we've been walking toward. So there's the job. Stand out in the field, hold up your frame, and tell me how many lines pierce it.
Count them. So I'm to stand in a field of invisible push, holding up an imaginary picture frame, ticking off invisible lines one by one as they stab through it. 1, 2, 3, like a bouncer working the door of a club that doesn't exist. Give me a little clicker at least, one of those tally counters that go click in your palm.
Keep the clicker. You've earned the clicker. And yes, it sounds ridiculous, right up until the tally turns into a law you can lean your whole weight on. That count, the lines threading your frame, field strength times the square-on area, has a name. We call it flux. But before you fall for the word, hold one thing hard, because it's the commonest trap in the whole room, and the word itself is what sets it.
The word sets the trap. Let me guess it, because it's already springing shut on me. Flux, flowing. Flux sounds like flow. It's got me picturing something actually streaming through my hoop. A wind, a current, some stuff pouring across the frame. And I'll bet you're about to tell me nothing of the kind is happening, nothing's really flowing through it at all. The word is a bit of a liar. Am I warm?
Warm, and closing in fast. Nothing streams through your hoop. No air, no fluid, no substance of any sort crosses that surface. Not one thing physically moves through it. The wind was a crutch to get the picture into your head, and now I kick the crutch away. Flux is a counting device, nothing more. Field strength times perpendicular area, a tally of standing lines. The lines don't flow anywhere. They sit there in space, still.
Still lines, and I walk a counting frame past them. I take a census, nothing pours.
A census of the space. That's the whole of it. Strip the flowing out of the word, and only the counting is left standing.
So flux is a head count, not a flood. Nothing's moving, I'm only tallying how many lines pierce my frame, full stop. And the tally climbs two ways, the very same two dials as the window. If the field is stronger, the lines are packed tighter, so more of them cross the frame. Or if I turn the frame more square on, I catch more of the ones already there. Stronger field or squarer facing, more flux. Weak or edge on, less.
Those two dials, that's the whole meter. Now the step that gives this teeth. So far your frame's been an open hoop, a flat pane with a rim, the wind blowing clean through it. Close it up instead. Seal it into a complete surface. A bag, a balloon, a sealed box with no lid missing. A skin with a clear inside and a clear outside. and drop a single charge down inside the bag.
And now I don't count lines through one flat window anymore, do I? I count them through the whole skin, all the way around, everywhere they poke out.
A sealed skin with a prisoner in it. And a closed skin can ask a sharper question than an open pane ever could.
So it's the same idea, wrapped shut. Wind through one open pane becomes lines through a closed surface. And now there's an inside and an outside, which there wasn't before.
Which changes everything, so mind it. Tally the net lines punching out through the whole skin. Net, because it's closed now, so you have to watch which way each line is crossing. A line heading outward through the skin counts as a plus. A line dipping back inward counts as a minus. Add them all up with their signs, and the leftover is your net count. So, one charge inside, what does that net come to?
Out is plus, in is minus, add them signed, keep the leftover. And you've clearly got the answer in your back pocket already, from the smug way you set that up. But let me try to reason it before you tell me, because I don't think the trapped charge leaves the lines much choice. It sprays them out in every direction, and every one of them is trying to get away, off to infinity.
Every one of them running for infinity. Good. Now to escape the bag, there's a sealed skin in the way. What must each line do on its way out? It can't reach the wide world outside without doing one particular thing to your surface.
It has to punch through the skin. There's no other way past a sealed bag. Every line the charge makes has to stab through the surface somewhere to get out. So, if I count all the lines poking out, I've counted every line the charge produces. And since the number of lines is tied to the charge by our fixed rate, counting the lines out is really counting the charge inside. The count is the charge.
The count is the charge. You carried it over clean. Now here's where I want you to gamble, because the next part ambushed everyone the first time they met it. You sealed the charge in a tidy round balloon and got your count. Keep the same charge, but crumple the bag. Make it lumpy, lopsided, dented, spiked. A crushed paper sack with fingers of it poking in and out every which way. Same charge, far uglier skin.
Same charge, hideous bag, and you want me to bet before I reason? All right, I'll bet, and I'll bet big.
Reason it to me then. Does the crumpled monstrosity give a different tally than the neat balloon did, or the very same?
Bigger. The ugly bag has to give a bigger count. Look at the thing. All those dents and spikes mean far more skin, far more surface for lines to stab through, and every crinkle is a fresh chance for another line to poke out. The smooth balloon is the tidy minimum. My horrible, crumpled, crisp packet, with fingers of it jabbing out in all directions, is a colander. It has to catch more lines. Lumpier bag, bigger tally. Final answer.
Confident and wrong, which is the finest way to be wrong. Watch one single line, right down near one of your spikes. It pokes out through the tip of the spike. Plus, one line out, good. But to get to that spike, it first had to dip inward through the dent sitting right beside it. Minus one line in. Out through the tip, in through the dent, and the two of them cancel dead.
Out at the tip, in at the dent, and they kill each other off. So the spike was never a free extra hole after all.
Never free. It sells you an exit and charges you an entrance, and the bill comes to nothing.
Ah, so my colander was double counting itself, and I fell for it whole. The ugly bag really does have more holes to stab through, sure, but half of those stabs are lines heading the wrong way, dipping back inward, and they subtract themselves right off again. Every crinkle I crumpled in adds its outs and its ins in matched pairs, and the pairs cancel. All that extra surface pays for itself and comes to nothing net.
Nothing net, however badly you maul the bag. So say it back to me as a rule. What did all your crumpling actually buy you?
Not a thing. Let me say it plain. The bag's shape is a red herring. Only what's trapped inside sets the count. The skin around it can be any shape I please. A tight little sphere, a sack the size of a house, a horror of dents and spikes, all the same net count, so long as the same charge is sealed in. My freedom to crumple bought me exactly 0.
Exactly 0. And it goes further than shape. It doesn't even matter where inside the bag the charge sits, dead center or shoved right up into one corner against the wall. Same net count out every time. The skin is entirely your free choice. The charge within is the fixed fact. Now let me push your luck the other direction, because there's a second surprise waiting right beside the first one.
A second surprise. Naturally, you never hand me one twist when 2 will do the job.
2 is the going rate with me. And this one turns the question inside out. Not where the charge sits, but which side of the skin it's on.
Go on, push it. I'm braced this time.
Take the charge and move it just outside the bag. A whisker past the skin, pressed right up against the outer wall, but out. Not sealed in anymore. So reason it for me again. That charge sitting a hair's breadth outside, drenching the near wall in its lines. What does the bag tally now?
Well, it's got to count for something, surely. It's a hair's breadth away. The near wall of the bag is getting absolutely hammered, floods of lines pouring through it. I can't believe a charge that close reads as nothing, only because it happens to be sitting a whisker on the wrong side of the skin. My gut says it mostly counts, maybe a touch less than fully sealed in, but that wall is drenched. The tally can't come to nothing.
That near wall is getting hammered. You're dead right about that half of it. But follow the lines the whole way through the bag, not only to the wall where they arrive. A line from the outside charge stabs in through the near wall. Minus 1 line in. It crosses the empty inside of the bag. And then it has to leave, doesn't it? It stabs out through the far wall on the other side.
Plus 1 line out, so it comes in the near wall and goes straight out the far wall, and those two cancel, minus and plus. And that's true of every single line from that outside charge, isn't it? Each one that enters the bag also leaves it. In equals out, line for line, so the whole flood cancels itself. And it holds even for one of my hideous spiky bags. Let an outside line stitch in and out through the dents as many times as it likes, and with no charge sealed inside for it to end on, it still leaves exactly as often as it enters. Every in matched by an out, so the whole stitched path sums back to nothing. The bag never keeps a single one.
The net comes to nothing. So the bag is completely blind to anything sitting outside it. An outside charge just threads its lines straight through, in one side and out the other, and contributes 0 to the net count. A charge inside, its lines get out and never come back, so they tally up. A charge outside, in and out, cancelled clean. The count only ever hears about what's sealed in.
Deaf to the outside, all ears for the inside. The skin's a snitch that only ever tells on its own prisoners.
Only its own, and a snitch with a very short list. Everything past the skin, it treats as though it simply weren't there.
So there's the pair of facts sitting side by side. Inside charge counts fully. Outside charge counts for nothing at all, no matter how close it's pressed to the skin. And I get the feeling this pair is what all the counting was driving at. This is the law, isn't it? This is what the counting hardens into. So give it to me whole, with a name on it.
It carries a name, Gauss's law. And here's the clean version to keep. The net number of field lines poking out through any closed surface depends on one thing and one thing only: the total charge sealed inside it. Not the shape of the surface, not its size, not where the charge sits within, and nothing outside it at all. Net flux out equals the charge enclosed.
Net flux out equals the charge enclosed. That's a tidy little sentence for something that felt so slippery 20 minutes ago. Though I want to poke at the equals sign. You said the flux equals the charge, flat like that. Is it truly 1 for 1? A given lump of charge and outcome precisely that many lines. No fudge, no conversion. Or is there some quiet number of nature sitting in the middle, setting the exchange rate?
There's a quiet number of nature sitting right in the middle. The net flux out equals the enclosed charge divided by a fixed constant. A constant baked into empty space itself, the same everywhere in the universe, that sets how much field a given scrap of charge is entitled to make. Tonight we keep it in plain words and never mind its size. It's the exchange rate on the counter.
An exchange rate baked into empty space, the same on the far side of the sky as in this room.
You don't get to set it. The universe set it, and then walked off.
So the bones of the law don't care what that number is, the shape of the thing is. Lines out, charge within, tied together, and nothing else in the world gets a vote. And that's the part that ambushes me, looking back. I counted invisible lines through a made-up bag, a surface I invented and drew wherever I pleased, and out of all that pure invention fell something rock-solid and real, the exact charge inside. How does invented bookkeeping pin down a real fact?
Because only the bag is invented, the counting isn't. The field is real. We spent the whole of last time earning that word. Real lines, set by a real charge, standing out there whether or not you ever draw a single bag. You're free to sketch the imaginary skin anywhere you like, but wherever you sketch it, every real line from that charge still has to cross it to escape. Your freedom and the world's grip never fight.
So my freedom and the world's fact live on two different things. I own the bag, the world owns the lines, and they meet in the count. My choice can't spoil the answer because whatever surface I draw, the same real lines have to pierce it. All right, I believe it now, properly, but I want to put it to work, because so far it feels backwards from what I'd actually want in my hand.
Backwards how? Tell me the shape of what you want, and let's see whether the law bends that way.
Usually I already know the charge. There's a charged ball right in front of me. I know what's in it. What I don't know, and would give my eye teeth for, is the field, the strength of the push, out there at some particular distance from the ball. The law hands me the charge when I know the lines. Can it run the other way, and hand me the field when I already know the charge?
It runs both ways, and running it backward is where it wins its fame. But there's a catch worth naming plainly first, because this trick is easy to oversell. Gauss's law is always true. Every bag, every charge, no exceptions, ever, anywhere. What it is not, always, is useful. It only turns into a shortcut when you're clever about which bag you draw around the charge.
Always true, but not always helpful. So the whole skill is in the choosing of the bag. And I think I can see the shape of a good choice. If I could pick a surface where the field is the same strength all over the skin and poking straight out through it everywhere, then the counting would go easy. The flux would only be that one strength times the whole area, and I could turn it around and solve for the strength.
That's the entire game. The way you force the field to behave that nicely on your surface is to match the bag to the charge's own symmetry. Give a symmetric charge a bag with the same symmetry, and the field has no choice but to come out even and simple on the skin. So take the roundest case there is, a single point charge or a nice round charged ball. What bag do you reach for?
A round one. A sphere centered right on the charge, and I think I even see why it works. If the whole setup is perfectly round charge, round bag, dead centered, then the field can't play favorites. There's no direction for it to prefer, no reason to be stronger off to one side than another. So it has to be the identical strength all the way round my spherical skin, poking straight out through it, square on, at every single point.
No lopsidedness anywhere for the field to hide in, so it comes out flat and even everywhere on the sphere. And now feel how that guts the counting. The flux out is the field strength times the sphere's whole area. One number times one area, because the strength is the same all over and every line pierces square on. No mess of different values to add up. And Gauss says that whole thing equals the charge inside over our constant.
Field strength times area on the one side, charge over the constant on the other. Two quantities I can lay against each other.
Two quantities, one equal sign, and you know all of it but the field. So do the obvious thing to it.
So I set them equal and turn it around. And the field strength out there is the charge shared out over the area of my sphere. The push at any distance I like, handed to me almost for free. I only had to know the charge and pick a round bag. That's the counting law running backwards, paying me the field in exchange for the charge I already knew. No grinding, no sweat. That's a proper conjuring trick.
A proper conjuring trick, and it's why Gauss's law is a workhorse and not merely a pretty statement. It hands you fields you'd otherwise sweat blood for.
Hang on though, wait. A while ago you made me swear on my life that the lumpy crisp packet gives the very same count as the tidy sphere. Same answer, any bag at all. So the sphere isn't special, is it? It's not that the round bag knows some secret the crumpled one doesn't. It's only the one where the arithmetic happens to be a gentle stroll instead of a nightmare. The sphere's been showing off this whole time. Same answer as my ugly bag. It merely wears a nicer suit to hand it over.
A nicer suit? That's the whole of it, and it's worth sitting in. On the crumpled bag, the field is a different strength at every dent and spike, pointing a different way everywhere you look. So the count is a brute to add up, even though the law holds on it flawlessly. On the sphere, the field is one strength, one facing, the same everywhere at once, so the count folds down to a single multiplication.
One multiplication against a whole lifetime of adding up dents. I do see why you reach for the round one.
Anyone would. The same truth sits on both bags, but only one of them lets you go home for supper.
So the lumpy bag is true and useless, and the sphere is true and easy, and they give the identical answer. The sphere only gives it to you without the misery. Symmetry never changes the law one whit. It picks the bag that does your arithmetic for you. That's a humbler job for the sphere than I'd have credited it with. It's not doing the physics at all, it's doing the paperwork.
It's doing the paperwork. I'll keep that. And here's a small gift that falls straight out of the round case, one worth pocketing. You asked for the field around a charged ball. Does it matter, out where you're standing, that it's a fat, solid ball rather than a single tiny point? You'd think a spread-out ball and a pinprick of charge would feel different. From outside, you cannot tell them apart at all.
Can't tell them apart? A whole spread-out ball of charge and a single tiny point. Read the same from outside? That seems like it's getting away with something.
It gets away with it completely. A uniformly charged ball, seen from any point beyond its surface, makes precisely the field of a lone point charge sitting at the ball's dead center, with every scrap of the ball's charge scooped into that one grain. You'd never know the difference from where you stand. The round symmetry lets the fat ball masquerade, from outside, as a single point.
So the ball hides behind a point, one less thing to ever worry about, good. But now I want to break the roundness on purpose, because the world is not all neat little spheres. Suppose the charge is smeared out flat instead, a great charged sheet, a charged wall stretching off endlessly in every direction, no edges anywhere. There's no center now to aim a sphere at. So what bag do I reach for? And what does the field do as I back away?
Flat charge wants a flat-faced bag. Picture a little drum, a pillbox, a short round tin, poked straight through the sheet, so one flat lid sits out in front of it and the other lid sits behind. By the symmetry, the lines leave the sheet straight out, perpendicular, dead even, piercing the two lids and merely skimming harmlessly along the drum's curved rim. All the counting happens through the two flat faces.
Two flat lids doing all the counting, and the curved rim only along for the ride.
The rim's the interesting part, actually. Picture how the lines meet that curved wall as they leave the sheet.
So the rim contributes nothing, because the lines only graze along it edge on, no flux through the sides. So I count the two lids, set that equal to the charge caught inside my little drum, and solve. And out comes the field in front of the sheet. Go on then, what is it? What does the push actually do as I walk backward, step by step, away from an endless charged wall?
Here's what drops out, and brace for it. The field out in front of an endless sheet is the same strength no matter how far away you stand from it. Step back a pace, step back a mile. The push on you does not fade one bit. It's flat and even and utterly indifferent to how far off you've walked. The endless wall pushes you exactly as hard from across the room as from up against it.
Wait, no, that can't be right because everything fades. Last time you drilled it into my skull that the push drops off hard with distance, a quarter of it at twice as far, the square of the distance doing all the damage. Now you tell me I can walk a full mile back from this sheet and the push is every bit as strong as it was pressed against it. Nothing weakens? That breaks the one rule I actually thought I'd nailed down cold.
It breaks nothing. It teaches you what the fading was ever really about. Think about why a push fades at all. It fades when the lines get room to spread out and thin. Back away from a lone point charge, and its lines fan out wide into open space, thinning fast as they go. And there's your steep fall-off, drawn as a picture. The thinning is the fading. So the sheet must somehow never let its lines thin.
Right, so where does the endless sheet's crowd of lines get to thin out to?
Nowhere. And that's the whole answer. Back away from an endless sheet, and the lines have nowhere to thin to. Step back a pace, and there's always yet more sheet stretching off to the sides, feeding in fresh lines to fill any gap that opens. The crowding never eases because the supply never runs dry. Endless sheet, endless supply of lines, and so no fade at all. The density just holds.
The supply never dries up, so the crowd never thins, so the push never drops. An endless wall, an endless shove.
An endless shove at any range, which sounds mad until you see it's only the lines never being let spread.
So the fading was never about distance for its own sake, it was about the lines thinning as they spread, and a sheet that runs on forever simply never lets them spread. Which means the whole fall-off must depend on the shape of the thing making the field, on how much room the lines get to fan out into as they leave home. Point charge, loads of room, fast fade. Endless sheet, no room, no fade. So what lives in the gap between those two?
You tell me. Reach for the shape that's neither a lonely point nor an endless flat wall. The in-between thing.
Something long and thin, I suppose. An endless charged wire. A straight line of charge running off both ways forever. More spread out than a point, but nowhere near a whole sheet. So it should fall somewhere in the middle. Fade, but not as hard as the point does. What bag do I wrap that in? And how does its field die off as I step away sideways from it?
Long and thin wants a long round bag. Wrap the wire in a cylinder, a tube, sharing the wire's own axis, capped at both ends. The lines shoot straight out sideways from the wire, all along its length, piercing the curved wall of the tube everywhere around it. And now watch how they get to spread as they leave, because it's only halfway free. They fan out sideways, out around the wire, but never forward and back along its length.
Because the wire just goes on and on, so there's always more of it in that direction feeding in. The same trick as the sheet, but only along the one axis. So the lines spread out just in a circle around the wire, opening up like ripples widening on a pond, and that circling is the only spreading they get. One direction's worth. So that should give a fade, but a softer one than the points.
a softer one. The field of the endless wire drops off as 1 over the distance, plain distance, not as the square of it. So walk twice as far from the wire and the push halves rather than dropping to a quarter. It fades, but far more forgivingly than the point charge does. The wire sits neatly between the sheet that never fades and the point that fades hard. A middle child in every way.
So now I've got 3 cases lined up and 3 completely different fades. The endless sheet, no fade at all. The endless wire fades as 1 over the plane distance gently, and the lone point charge fades as the square of the distance steeply. Same counting law every time, counting the very same kind of lines, and the only thing that changed between them was the shape of the charge. There's a pattern in that I can almost taste on my tongue.
Then taste it out loud. What's the one thing marching through all 3?
It's about directions, about how many ways the lines are allowed to fan out as they leave. The sheet's lines march straight out and don't spread in any direction, so no fade. The wire's lines spread just sideways, in 1 circle's worth of directions, so a gentle fade. And the point's lines spread every which way at once. That's got to be the most spreading there is, in every direction available. Which must be why it fades the hardest of the 3.
Every which way at once, over a whole swelling ball around the charge. And that last case, the point spreading over a growing ball, is the one worth opening. You built the ledge right up to it yourself, 3 cases in a row. So let me tell you exactly why the point charge fades as the square of the distance and not as anything else at all.
Then tell me, point charge, lines spraying out in every direction, spreading over a swelling ball as I back away from it. What actually drops out when you finally sit down and count them?
A fixed number of lines leaves the charge. Fixed because the charge itself is fixed, and the charge is the only thing that sets it. Now take that same unchanging batch of lines and ask them to cover a whole sphere out at whatever distance you're standing. As you back away, the sphere they have to cover swells. And here's the fact it all turns on. Don't take it on faith, feel it. Blow a photo up to twice the width and it drinks 4 times the paper because both sides double at once. A ball's skin is no different. Twice as wide, 4 times the surface. A sphere's skin grows as the square of its radius, and that square is the hinge of the whole thing.
As the square of its radius. So the skin doesn't only grow as I back off, it grows in that particular steep way.
In that particular way. Go twice as far out, and the sphere's skin isn't twice as big, it's 4 times as big. Go 3 times as far, and it's 9 times. The same fixed batch of lines, now smeared over 4 times the area, or 9 times the area. So they thin to a quarter, or to a 1/9. And the field, which is only the crowding of those lines, thins right along with them.
Oh, that's it. That's the whole thing, isn't it? The square in the inverse square was never some separate fact anybody had to go out into the world and discover. It's the square in the area of a ball. Twice as far, 4 times the skin, a quarter the crowding, a quarter the push. 3 times as far, 9 times the skin, a 1/9 of the push. The field fades as the square of the distance because a ball's surface grows as the square of the distance. And it's the same square, the very same one.
The very same square. And you reached it yourself. Now let me settle a debt from last time. I made you hold a phrase on the way out the door and promised it would come back wearing a different coat. The push spreads thinner and thinner over something that keeps growing. There it is, and there's its coat. The something is the surface of a ball, and it grows as the square of the distance out.
The coat is a ball's surface, and a ball's surface grows as the square.
The phrase was the answer, waiting in plain sight. I only made you carry it until you'd built the thing it was describing.
So Coulomb's inverse square law, the thing I met last time as a steep, slightly ominous rule about 2 charges shoving each other, was never really a law about a force reaching across a gap at all. It's what you get when a fixed spray of lines has to share itself out over more and more room, and the room happens to grow as a ball. The steepness isn't in the force, the steepness is in the shape of space.
The steepness is in the shape of space. Coulomb's law falls out of the geometry, not the other way around. And that cracks open the thing I left glowing on the shelf last time, the one that gave you the actual chills. You had them, if you remember, so say it back and see if it still feels eerie now.
The chill was that Newton's gravity fades with distance in the identical shape, the very same square, even though it's a wholly different force that only ever pulls, never shoves. And now I think I see why they agree, and it's not eerie at all. If gravity also sprays some kind of lines out of every lump of mass, spreading over the same swelling ball as they go, then of course it fades the same way. They just live in the same space.
They live in the same space, and that dissolves the whole coincidence because there wasn't one to begin with. Mass sprays its own lines, gravity obeys its own version of this very counting law, and its field thins over the same swelling ball that yours does. Two utterly different forces, one geometry underneath. Anything at all that spreads out from a point into three-dimensional space, sharing a fixed something over a ball, has no choice in the matter.
No choice, it must fade as the square, because the ball it's spreading over grows as the square, full stop. So the inverse square law isn't really a fact about electricity, and it isn't a fact about gravity either. It's a fact about space having 3 dimensions. That's a wildly bigger statement than the one I walked in with. I came in with a rule about balloons, and I'm leaving with a rule about the shape of the world.
A rule about the shape of the world. That's the size of it. And notice, the sheet and the wire fall into their places under the very same idea. The point sprays into all 3 dimensions, over a ball, and fades as the square. The wire spreads sideways only, into a ring's worth of directions, and fades as the plane distance. And the sheet gets to spread in no direction at all, and so doesn't fade one bit.
Ball, ring, nothing. I can say it back, but let me push once before I swallow it whole. Is that a real explanation, or have I only handed the same 3 mysteries a tidier name and called it a day?
A fair shove, and here's the difference. A name only relabels. This predicts. Hand me any new shape and tell me one thing, how its lines get to open out, and I'll tell you its fall-off sight unseen. That's not a fresh coat of paint. That's the idea doing work.
So it was never 3 separate mysterious fall-off laws that I'd have had to memorize as unrelated facts handed down from nowhere. It's one single idea. Count the lines, watch them spread, and the fade reads straight off how many directions the lines were free to fan into. One dimension of spreading gives the gentle fade, none gives no fade, all of them give the steep one. That's so much tidier than a whole pile of rules.
One idea, read off 3 ways. And notice what you did a moment ago without a flicker of worry. You set out from Gauss's counting law, lines through a bag, and out the far end fell Coulomb's inverse square entire, the force and its fall-off together. That's no accident to shrug off. For charges sitting still, Gauss's law and Coulomb's law are the same physics in 2 costumes. Not 2 forces, one single fact about the world, packaged either as a push between 2 charges across a gap or as a tally of lines through a surface. Start at either, and you walk yourself straight to the other.
So they're genuinely the same fact in 2 outfits. I met them as 2 separate animals, and they turn out to be one. Which makes me ask the blunt question then, why keep both? Coulomb was already sitting in my pocket from last time, perfectly good. If this counting lines through a bag business tells me nothing new about the world, why spend a whole night making me learn the second outfit? There has to be something it does that the plain push simply can't.
2 things, and the second is the large one. The first you felt in your own hands tonight. Ask Coulomb for the field of a whole charged sheet, or a wire, or a ball, and you're in for a brutal grind, piling up countless tiny pushes, one weary charge at a time, where Gauss handed you all three in a single line each. The second is that this counting version is the one that grows up. Flux tied to the charge that makes it turns out to be the first of four great laws that by the end of the course fold together into a single picture of everything electric and everything magnetic. And somewhere in the knot where those four meet sits that travelling ripple I promised you last time, the shiver that races off a jiggled charge and turns out, when you finally corner it, to be light itself. But that's a door for much later.
Light, waiting at the end of four laws. You're doing the thing again, dangling the treasure, then walking off into the dark. Fine. I'll leave it up on the shelf beside the other shiny things you've hung there and refuse to explain. But it does leave me standing somewhere genuinely new tonight, and I want to mark exactly where I'm standing before we step out of this one.
Mark it then. Where do you stand now that you didn't this morning, before any of this?
I came in able to draw the field but not do a single thing with it, and now I can count it. And the counting told me how strong the field is, everywhere, for all sorts of shapes. So I've got strength in hand at last. What's the next thing worth wanting, once you already know how hard the field pushes at every single point in the room?
You spent tonight asking how hard it pushes. The next thing to want is what that pushing costs you. Take a charge and shove it through the field, straight against the lines. You have to do work, real effort, the way you sweat hauling a weight up a hill. And let it go the other way, along the lines, and the field does the work for you, like a ball you've set rolling down a slope.
Push against the lines, and I spend, go the way they point, and I'm handed a free ride downhill.
Spend on the climb, coast on the drop. And the field keeps a strict tally of every last bit of the effort.
Work against the lines, coasting along with them. And that ought to ring a very loud bell, because that's the whole spine of the mechanics course come back around. Hills and valleys, an energy landscape. Climbing costs you effort, dropping pays it back, and the terrain keeps the books on where the effort went. You're telling me that same landscape returns here, only now the hills and valleys are built out of charge and field instead of gravity and height.
Built out of charge and field, exactly the same landscape underneath. So moving a charge around the field becomes a walk across that hidden terrain, spending effort as you climb against the push, banking it back as you drop along with it. And the height on that landscape, the thing that tells you how steep the climb is and how much a charge would spend making it, that height has a name of its own.
And I'll bet it's a name I already say out loud without the faintest idea what it really means. The way I said charge for years while pointing vaguely at nothing. Go on, put me out of my suspense. What do we call the height on this hidden landscape you've just built for me out of the field?
We call it voltage. The height on the field's landscape, how much work a charge spends or banks, moving from here to over there. That's where we pick things up next time, the field's landscape and the thing we call voltage. Tonight you learned to count the field and found a law hiding in the counting. Next time you learn to walk it and find the hills. But the last word is yours. It always is, at the door.
Then here's the shape I'm carrying out. I walked in with a field I could only stand back and admire, and you taught me to count it. And the counting turned out to hide a law, and the law turned out to hide the shape of space. But the one that actually stood my neck hair up was the inverse square. That steep, ominous fade I'd taken for a brute fact of the universe turns out to be nothing but the shape of a ball, a fixed spray of lines, sharing itself over a sphere whose skin grows as the square of the distance. Twice as far, 4 times the skin, a quarter the push. Coulomb was geometry the whole time, and so is Newton's gravity, for the very same reason. Lines spreading out into 3-dimensional space have no other choice. So the next time something fades with distance, I won't ask what's draining away. I'll ask what shape the lines are spreading over, because the fall-off was never in the force. It was in the room. That's the one I'm keeping. See you next time at the landscape.